So today we'll just kind of introduce machine learning in very broad parameters and thoughts about applications, different types of machine learning, and also we'll discuss ethics surrounding machine learning. And then for the most part, the most prevalent use of machine learning that differentiates machine learning from sort of other quantitative statistical methods that we use in scientific research is their facility at prediction and using them for like comparison of different methods through prediction. So we'll talk about predictive methods with machine learning today. Okay. All right, so we all encounter machine learning applications on a day-to-day basis, right? If we're online, if we're on a social media platform and we're being fed individualized advertisements, the back end is a machine learning algorithm that's predicting what types of advertisements will work for you individually or individuals like you. If you have photos on social media that are being auto-tagged or tags recommended for them, there's a machine learning algorithm at the back end that's doing that prediction and suggesting those tags. Whenever you use GPS, the route is optimized using machine learning for predictions about traffic and traffic conditions and weather conditions and things like that. If you are encounter some emails going to spam or not, and you ever see something that shouldn't go to spam but does, that's a machine learning algorithm failure. It's predictive failure on the part of these backend algorithms that are doing prediction. And of course, if you have a smart speaker, just in case anyone has one going right now, I won't say the wake name for any of them, but if you have a smart speaker that acts as a personal assistant, then when you speak, it's using machine learning algorithm in the back end to predict what you're saying. Of course, there are very high-stake applications of machine learning as well, including guiding self-driving cars. You have machine learning algorithms that are used in tuning robotic surgeons, and also guiding the use of major scientific resources by doing sort of automated control of telescopes and equipment like that. So there are a lot of different everyday applications of machine learning, even outside of scientific applications. Okay, and the really exciting thing about machine learning is it's becoming very, very accessible. It's feasible to apply for anyone with basic programming skills because it's available across many languages, whatever kind of software that you use or statistical program. Chances are there's a machine learning library that can do 90% up to the state of the art in machine learning. AI assistants, different coding assistants. You have Copilot on GitHub. ChatGPT is not that bad. Can help a lot with coding tasks. And it's just a very practical methodology for addressing a large variety of questions with data. You have a lot of ways that you can get trainings for machine learning. So the traditional approach, this is where I got my first training in machine learning, was a course called data mining in the computer science department at UNC Chapel Hill, is to take those courses in computer science departments. But you can find courses now in the social sciences, natural sciences, statistics has a lot of statistics departments have courses on machine learning. And then, of course, online workshops or tutorials. And I think the growing availability reflects the demand for these kind of skills. Okay, so a lot of these applications that we see of machine learning are sort of controversial. Individuals in the public don't like the idea of having their attributes and behaviors predicted. And this has been an interesting development for a lot of tech companies that know the value in their products basically comes from the effectiveness of these predictions. So this is just a survey run by Pew several years ago that just asked people whether or not they thought like algorithmic decision making was good in these domains. And you see across each one of the applications, a majority of people said that it was unacceptable. It's not something that we should be using algorithmic decision making for. And of course, algorithmic decision making is used in all of these domains, and in a lot of them, it's pretty clear that they are that this is a very effective potential use of machine learning. So yeah, there was an interesting thing that happened when I was early on in my academic career with Facebook. At first was pretty collaborative with researchers as a company, and they would allow researchers to conduct collaborative research, and it kind of showcased the power of their platform. But in the 2008 presidential election, what they did was they allowed researchers from UC San Diego to participate in a study where they allocated individuals who logged on to Facebook either to treatment and control group, where those in the treatment group saw information about, like, organized information about their friends who had indicated that they were voting or they had voted or were going to vote. And in the study, the researchers who were running the study found that people were more likely to search out their polling their polling locations if they were in the treatment group, where they saw which friends of theirs had gone out to vote already. And they published this paper in one of the major journals, Prestigious National Academy of Sciences. It was a big publication for the researchers who conducted it. And the reaction in the public was very negative, because people were saying, well, the online platforms are experimenting with our behavior, and I might go out to vote or not vote because of what was shown to me online. That was kind of a frightening context for a lot of folks. So the reaction, right, of the platforms to this kind of negative publicity was, of course, not to stop doing it. This is the kind of testing of their platform that they have to do to see if they can change human behavior in ways that affects their bottom line. But they just kind of closed up collaborations with researchers such that they could no longer do collaborative experiments with these online platforms. And that's sort of where we're at today. Okay, so when we talk about algorithms, machine learning algorithms, or algorithmic decision making, sometimes the phrase that algorithm can be kind of intimidating. And I just want to demystify a way to think about an algorithm or a process that you're walking through with data analysis. So they're not as complicated as they sound. They're simple, like step-by-step process where they're just sort of spelled out from beginning to end. And you can think of them as like recipes used by chefs, right? Each step in a recipe is like a process in an algorithm. And once you follow the instructions, it leads to a final product. So if you can write down a recipe for what to do from input to output with data, that's an algorithm. Okay, so just kind of talking through a couple of detailed applications where you might want to use machine learning for doing prediction. So power companies can use it for just estimating what customer bills are going to look like. This ensures accurate billing, and you can flag like bills that are wrong or miscalculated with a predictive algorithm. So you can train an algorithm on household electricity usage data, and then provide monthly bill estimates for new customers. I'm a political scientist, so I'm very familiar with these applications. The machine learning algorithms are used pretty extensively in political campaigns for identifying voting patterns. So the goal is to discover unknown voter types and motivations, especially for getting out the vote. So they can analyze survey data using machine learning, and this provides insights into get out the vote targeting, which of course in political campaigns and motivating people, the best strategy that a campaign can take is finding those individuals who are likely to vote for their side if they are motivated to get out and vote. It's very difficult to persuade someone to vote for the opposite side. So it's more effective to find those individuals that if the campaign allocates resources to getting them out to vote, they're more likely to support their campaign. And one of the interesting things about this data collection for targeting voters is that actually the most effective data for predicting what an individual would do if they were to go out and vote tends to be like consumer behavior data. So for example, the political campaigns are big customers for the like grocery card data that people generate when they shop at grocery stores. So if anyone's used like a discount card to get coupons and so on when you go to the grocery store, that data gets linked to your individual profile and whatever you've given to the grocery store for that card. And then that data is sold to marketers, but also political campaigns, because they can use the profile of what someone has purchased at the grocery store as a pretty effective predictor of which political campaigns are likely to support, which is pretty interesting fact. Okay, so machine learning has seen like a lot of development over the years. So in the early stages, it was developing algorithms, training algorithms to play games. So key development in the late 1950s, early 1960s was developing algorithms to learn how to play checkers, the game of checkers. The essence or the concept of machine learning is distinguished from traditional AI. So traditional AI is based on programmatic rules and example of classifying animals using if-else statements. And traditional AI is sort of rule-based, and machine learning is algorithmic learning and adaptation. You learn in machine learning, you do estimation and training much more than in traditional AI, which is kind of just writing out rules of decision making. So we'll talk about this in a moment, those have kind of converged and blurred with the recent generative AI, or this idea of using machine learning models to inform the decision making in artificial intelligence. Okay. So models and algorithms, we'll talk about these things somewhat interchangeably, but they are kind of distinct processes. So we use models a lot in machine learning. A model is a set of rules that are learned by an algorithm. The rules can be reflected by parameters in the traditional kind of statistical sense. It makes predictions for new data based on the rules, and they simplify real-world phenomena for interpretation and understanding. Similar to a physical model, like a model of the Eiffel Tower, and statistical model is a simplified representation, okay, of the data. And of course, we have the famous quote, all models are wrong, but some are useful. So we make compromises in assuring that models are wrong in order to reduce them to something that is interpretable and interesting. So an algorithm is just a process by which a model is learned. So we have algorithms for training and for estimating models. And an algorithm is just a sequence of operations that we'll use to solve a problem of training, an estimation problem. Okay, so there are a lot of different methods and algorithms that we can use for any machine learning task. Anything that you want to do, multiple algorithms will exist for the same problem. You have different approaches that are developed to improve upon different methods. And then there's also like the famous no free lunch theorem, so no algorithm is going to universally outperform all others and all problems. And we need to put in the effort to identify the best algorithm for a particular task. So a lot of machine learning methods will get characterized as sort of black box, or even phrased to characterize as oracle methods. But we still need to look at each algorithm and select and test multiple algorithms that are known well for a similar problem, and evaluate the best performing method for a specific task that we want to complete. Okay, so we have a variety of different classes of machine learning algorithms. So there is supervised learning, unsupervised learning, and semi-supervised learning. Y'all may have heard of these different distinctions before. And supervised learning is the most prevalent type of machine learning, or something that's most commonly identified as machine learning. This is, we're trying to categorize data into predefined classes, right? We're trying to predict, is someone a voter, or are they not a voter? Is something a spam email or not a spam email? So we have these predefined classes that we'll use for prediction. Also regression, trying to predict someone's income, or their or trying to predict the casualties are going to happen from a given conflict, if you're in the context of doing militaristic applications of machine learning. Then there's unsupervised learning, which is just dimension reduction, or summarizing the data in interesting ways. So simplifying the complexity of data, or clustering, grouping the data into different groups without necessarily having predefined classes. Okay, so here's another example from Pew that is a supervised learning method. And so this is an example of supervised learning. And what they were trying to do was predict which voters were going to support which candidates, and use the predictive algorithm for that. And so they were just comparing different methods here for, so they had the benchmark as the actual outcome. And we're trying to use different machine learning algorithms to see which algorithm would get them closest to the accurate prediction. And so they compared random forest, which is a type of machine learning algorithm that we will learn about throughout the session this weekend. And then there's logistic regression, which some of you may have heard of. It's another way for predicting binary outcomes, which candidate a voter supports, using like a regression type equation. So they were just comparing these methods, and this is a traditional supervised learning where they're trying to predict a predefined outcome. Okay, so if no one's ever seen a dendrogram before, it's a pretty neat visualization of hierarchical clustering. And so this is an application where Wormley et al. Take opinion surveys and attitude surveys from all across the world, and try to categorize countries into sharing different profiles of cultural values. And so as you go up levels in the dendrogram, you get groups that are further apart, but still close together at that level. So you can see that Sweden and Austria down at the bottom are very close together at that first level. So they share a close cluster in cultural values. But if you go up to the next level, then you include Sweden, Austria, the Netherlands, and Denmark. If you go up yet another level, you would have France also in that cluster. And so this is just hierarchical clustering. It's a way to organize data, again, not knowing the classes ahead of time. This is an example of unsupervised machine learning. Okay, so folks may have heard the phrase deep learning. So what's going on with deep learning? So it's a subfield of machine learning, of course. All deep learning is machine learning, but not vice versa. And It's risen in popularity over the last few years, and especially, of course, over the last year, because deep learning is the backbone of generative AI tools. So when you have data that is very large, deep learning can perform exceptionally well. And in order to train deep learning methods and actually to even use them, to even draw a prediction out of something like ChatGPT, you require a lot of parallelized computing power because you call into a very large and complex model. And so GPU computing, as opposed to CPU computing, enables broader application because GPUs have, whereas a large CPU cluster might have 10 to 20 computing cores on it, GPU can split up calculation onto hundreds or even thousands of different parallel computing elements. So GPU computing is enabling us to do more computing that can feed into deep learning. Okay, so I want to talk a bit about what are the fundamentals and impact of deep learning. So it utilizes neural networks. So if you see the phrase deep learning, the type of algorithm that's being used is a neural network. And I'll talk a little bit about what that looks like. So these are just functions of parameters that are connected together in large networks. If you, the most similar thing that I can think of, if you're familiar with regression modeling, is having models that have many higher order interactions, except in a neural network, the interactions are built in a hierarchical way and in multiple siloed areas. Okay. So the connections within the neural networks pass and process information. Now, the challenge with neural networks is interesting that, when I was coming out of graduate school, the field was largely seemingly pretty down on neural networks. They're a neat idea, but they would almost always overfit the data. So overfitting means that it seems to perform really well on the data that you're using to estimate it, but then when you try to predict some data outside of the data that you use to estimate the model, it doesn't predict particularly well. But now we know that these methods really shine in settings that allow pre-training on massive data. So basically, in order to get a neural network trained well in a way that's not overfitting for whatever setting, you really need an enormous amount of data. And ideally, you want to be able to then use that model on data that was very similar to the model it was trained on. Okay, so this is the example of the famous sketch of the neural network. It's called convolutional neural network that was used for the ImageNet algorithm. So this is classifying images. So something like, is this a picture of a pug or a blueberry muffin? That kind of task of identifying what is an image or what's in an image. And so Krzyzewski et al. Developed this ImageNet algorithm. And so what's going on here is that the final layer, the one that all the way over to the right here, is where the attribute of the image is predicted. And if you walk backwards all the way to the first layer, this is where the pixel information about the images is summarized. And each one of these intermediate bins represents a reorganization of the data and passing through based on different parameters. And so the data is summarized as just information about colors of pixels in the image. And then all of that information gets passed through and interacted across different layers of parameters. And so this is the characteristic if you're reading a deep learning paper using a deep learning algorithm, you'll probably see an image like this. And the depth is just a reference to how many different iterations of hierarchical interactions are built between the input data and the final output that is predicted. Okay. And so as you can see, each one of these layers, as they feed into each other, is going to cause the interaction terms between parameters to proliferate. And so you just need an enormous amount of data in order to effectively train this model. So this became really useful because it could be trained on large data sets of images, and then just used for other image classification tasks like recognizing people in images, or even emotion classification of faces that can be extracted from images. Martha.
So there was a question in the chat, and I would like to just highlight that on, because you've used large data and then you just used enormous data, and we're interested in what do you mean by large or enormous?
That's right. Oh, great question. Great question. So yes, I'll try to summarize that threshold there. So large data. So the kind of data that most of the methods that we're talking about today and that we'll see in the applications, data sets on the orders of hundreds or thousands of observations is perfectly sufficient for using these methods. When it comes to deep learning, what we're talking about right now, in order to develop the models that are going to perform accurately, we're talking about in the millions or billions, even more of data items. So, for example, the transformer model, one of the large language models, a precursor to ChatGPT, was trained on all of English Wikipedia. That was the training data for it, as well as a good portion of Google Books. So I don't have it in here. This is the ChatGPT. We don't really know what the training data is for ChatGPT, except for it's substantial. But the training data for the precursor to ChatGPT, the first transformer model to come out, which is called BERT, that was released by Google, was trained on the entirety of English Wikipedia and a good portion of Google Books. So there were trillions of phrases and text that were instances that were used to train that model. So there's a big distinction between training conventional supervised machine learning algorithms, the algorithms that we will focus on mostly during this workshop, and training or developing deep learning models. So for the most part, most people or organizations do not have access to data on the scale necessary to develop a new deep learning method. What is being done now with using pre-trained deep learning methods, and this is not a course where we're going to focus much on deep learning. It's I know that Statistical Horizons doesn't have a workshop on deep learning, but the way these models are used, such as GPT or BERT or ImageNet, is that the developers of the model publish the model parameters. And what researchers will do if they want to use a deep learning model will do what's called fine-tune that model. So they'll download the actual model and its parameters, and then use whatever relatively small data, and by small data could mean tens of thousands of observations that they have of their own data set, and use that to fine-tune the parameters. So update the parameters just slightly so that they better fit the applications of interest. So that's sort of how to think about deep learning versus conventional supervised machine learning. Supervised machine learning is perfectly applicable to data sets that are of common size in scientific applications. When it comes to deep learning, these are methods that are initially developed on very large scale institutional data. I hope that answers the question.
Yeah, great. Thank you.
Sure. Yeah, so ChatGPT is a deep learning method at the background. So if you ask ChatGPT about large language models, it will tell you that it is indeed a large language model. Okay, so it's important to think about ethics in machine learning because it is a very powerful methodology. And so we should kind of talk this through, and you want to think about what you're doing when you're developing machine learning methods and how they can be used and misused. Okay, of course, machine learning has a potential for both beneficial and harmful applications. Um, so it is so they in this study by Wong and Kosinski, they found that they could based on image data, they could predict sexual orientation of individuals and images. And at Google's image recognition bias, Google image recognition has a well-documented problem with classifying the race of people of color and being just more accurate in general for white people. So when you're developing a machine learning method, of course, it's important to think about predictive accuracy, but you also want to think about potential biases in the algorithm. So if an algorithm performs really well, but performs poorly for some subset of the population, then it's going to induce inequalities in that application. So you want to be thinking about that as you develop an algorithm for an application. Okay, and so there's a big question now with algorithmic decision making of who's responsible and what kind of responsibilities do we want to attribute to the algorithm and to those developing the algorithm. So data sets, you want to make sure that your data set, your training data set, is representative of diverse populations, that you test and evaluate models and then correct them for biases that could be built into the data and thus like built into the model. And you want to make sure that they're deployed in ways that are thoughtful to prevent misuse and harm. So this is an article from Wired about there are a lot of critiques out there of the use of crime prediction as a way to guide the allocation of law enforcement resources. And so, of course, if you're having law enforcement do patrols or investigations of problems in different areas, then if you can predict where crime is going to occur, then you can more efficiently allocate those resources. However, if the past arrests or the patterns of law enforcement behavior in the existing data reflect biases in law enforcement application, then those predictive algorithms are simply going to, by default, regurgitate those biases. And so you want to be, when you're developing and using algorithms like this, you need to be thinking about what kind of biases can arise. And typically, those are the biases that are already existing in the data. Okay. So you also want to think about how different algorithms can get out and then be used sort of in the wild. So deepfake technology can create realistic videos just from looking at images. It doesn't even need video to reproduce video. Of course, you can fabricate evidence or defame individuals. And Sojourn et al. have a good overall overview article on the potential risks of this. So with the use of data, you also want to think about how it's being consented to and how potential uses arise. So make sure that the data is collected and used in an ethical manner. They have informed consent for sensitive personal or financial data. And if anyone saw the Cambridge Analytica kind of scandal back in the 2016 election, of course, Cambridge Analytica was able to collect all sorts of backend data on Facebook users for political purposes that arose just through like the marketing interface on Facebook. So Facebook has since changed their policies on how individuals can access backend data about the users that their advertisements are being targeted at. But this is an important thing to think about is how the data can be used for different purposes than it was originally collected. All right, and who's at fault when something goes wrong with machine learning based decisions? So to what degree are humans involved in decision making? Should we rely solely on model predictions for doing things like sentencing or allocating police resources? Who is accountable when things go wrong if it's an algorithm making the decision? And so we need to make sure that we're balancing human judgment with machine learning insights. So it's crucial to think through and then come up with strategies for addressing the potential for misuse of advanced algorithmic technologies, for thinking through the ethical implications of data collection and usage, and also the role of human decision-making in machine learning applications. All right, so I would say you want to go through with any kind of machine learning project or technology that you're releasing, a few kind of reflective questions just to address these issues. So first, just are your intentions ethical, right? So if just because you can do something doesn't necessarily mean you should. Could the model that you're releasing be misused for harmful purposes? Is there any bias in the model that could cause harm or result in discrimination? Has the data been collected ethically and responsibly? And how would human decision-making integrate with the model once it's deployed? So how would you recommend that a model be used in human decision-making? Louisa?
Yeah, thank you. Can you all hear me?
I can, yep.
Okay, great. I have a question about this like third question, the bias in the model.
Mhm.
If working with administrative data, I think we can all appreciate that there are sometimes selection biases on who's in an administrative data set, particularly with US healthcare, and who isn't. So if you know going in that there is a selection bias in who's in your data and it's not representative of maybe the entire population in which you want to make predictions, does this mean that any sort of output from a machine learning algorithm is by very nature reflective of that same bias? And what can you do to really correct for that bias in selection?
Oh, that's a great question. And there's a whole subfield of sort of machine learning methods that comes up with different problems and methods to address this. But one of the most basic steps you can take is to try to identify differences between your data set, the training data that you have, and the population that you are targeting based on different representative demographics. So you can see what is the distribution of age, race, gender in your data, income, health status, employment status in your data versus the population. And one step that you can take is to resample your data or reweight observations in the training algorithms to more accurately reflect the population. That's sort of one step to addressing any kind of biases that might arise in what you're doing. So that's just sort of checking whether your data reflects the population that you're targeting. Another approach is to analyze the predictions that come out of the algorithm for varying levels of accuracy based on demographic attributes. And so one pattern that we see arising in a lot of different algorithms that are evaluated is that they don't perform particularly well among people of underrepresented racial backgrounds, simply by nature of if something like one of those complex neural networks, right, is going to pick up a lot of interactions in a data set. And one of the things that it might pick up that we don't really notice just from looking at the parameters is that there is some interaction between an individual's racial category and how other variables work in the model. And so if we don't see that on the development of the model, which is kind of hard to see in the way these complex models are estimated, what we can see is how accurate is this model at predicting, something like the success of a mortgage application and breaking that down by demographic categories to see, is this algorithm just as accurate for people from underrepresented racial groups as it is for white people in the sample. And so those are kind of the two ends. One, you can try to balance the input data to be more reflective of the population that you're targeting. The other is that you can analyze the outputs, the predictive outputs, to just double check whether the algorithm performs effectively for all groups. And then what you can do, if you do find that the algorithm is much more accurate for one group than another, is you can go back to the algorithm and tell it to place heavier weight on the group of observations that is, being poorly predicted by that algorithm, to say, give more weight to this underrepresented group in training the algorithm. So, Mehmet? Do you have a question?
Yes, I just have a kind of follow-up question on the same issue. I mean, when you analyze big data, insurance claims particularly, one of the first thing you do is actually you find a fit for purpose data set. And in many of my studies, basically, there are different payer categories are very important, particularly when it comes to mental health related studies. And in many cases, Medicaid is actually the right data source to go with it. And there are different data vendors providing data on commercial, Medicare, Medicaid, etc. But there are some data sources basically just mixing all these. So can you basically, so my question is basically like mental health covers almost 80% of mental health related, conditions and diseases, etc. But when you have a mixed data set, can you manually feed, that 80% of these patients are Medicaid? The remaining, even if the data source you're using is mostly commercial and some Medicare, Medicaid, etc. So those adjustments, can you basically using the national survey data results, basically for particular years or time frames?
Yeah, and so is the concern that since most of your data is coming from like Medicaid claims, that's not kind of representative of the population to which you want to apply the algorithm or the analysis? Is that the concern?
That is correct. So, I mean, basically, the data source, as I indicated, you already know that from the literature that the majority of your patients will be Medicaid, but you start using a data source which is basically, claiming that, oh, they are very representative, all payer types are there, but you know that 80% of your patients supposed to be on a very particular, payer category, and um, so basically, you can't just claim that, that particular Medicaid may be underrepresented basically on that data source or for a particular reasons. There are lots of things might be happening. So in cases like that, so can you actually manually make adjustments in your machine learning algorithms, etc.?
Yeah, in that case, you would want to reweight the observations in your training data for the expected, breakdown or distribution across Medicaid and Medicare participants that you would expect to see. So you can reweight the data to reflect the target distribution that you want to use a model for, given the data that you have access to. I understand that, it's hard to get access to claim data, insurance claim data. And then another thing that you want to look at is, do the predictions perform differently based on whether or not someone is a Medicaid participant? So whatever algorithm that you're trying to use, the potential for bias arises and is more acute if the prediction works differently for individuals who are and are not Medicaid participants. So you could analyze the predictions to see how they vary based on Medicaid participant status. And also, if you find a bias, you could go and reweight your sample to focus more or less on those individuals in your data based on how the model performs.
Thank you.
Sure. All right. Any other kind of questions or comments on this topic?
So I have a question. I think from what you described, machine learning applications provide the researcher with more freedom to try and experiment with different settings of the parameters or to fine tune it than, let's say, traditional statistical or econometric approaches might. I think this comes at the degree of sacrifice made with regard to explaining why you did something or the ultimate explainability that accompanies accurate predictions, right? I mean, for example, traditional models would always start with a theory first, and then the data is supposed to be used to test that theory. Here, we are so focused on predictions that there's really no theory, it's atheoretical. And when you find predictions that actually work, people don't really care about the theory. So I'm wondering whether machine learning models ever promote more understanding of how the world works, rather than they're so focused on predictions that it's at a cost of heavy sacrifice made.
Mm-hmm. Yeah, and so you've asked questions that we could spend all day talking about this. So there are many like good and important topics here, and we'll get into some of this a little bit more kind of systematically as well with the rest of the lecture. But so it is certainly the case that model development with machine learning is guided more by prediction than the goal of evaluating an explanatory model. And that can have some benefits and some significant costs. So one of the major costs, of course, is that because the models are so kind of complex and nonlinear and discontinuous in different ways, they're not easily interpretable. So for the most part, you don't get an estimate of like one clean estimate of the relationship between one variable and the other variables using machine learning methods. And so it's hard, even if you want to interpret it, it's hard to interpret it. And so one of the downsides of that can be, for instance, if you have a model that you're using to predict where arrests are going to happen, and that's guiding where police allocate their resources, and you don't have a firm understanding of what's going on in the model, it may be the case that past arrests are representing a lot of racial discrimination, and the model has just picked up on that racial distribution and is sending police to areas with higher concentrations of racial minorities. And so that can happen, as documented to be a pattern that has happened with predictive policing algorithms. But if we're not scrutinizing the explanation for why the model is making the predictions it's making, then we can fall subject to this kind of bias pretty easily. So that's certainly the case. Now, there are also upsides to focusing on prediction with machine learning methods relative to conventional models where you specify the structure and then just use the data to estimate parameters. In that, so if there is a strong nonlinear pattern in the data that you can pick up with a machine learning method, that then begs additional explanation. So if you think that a relationship should be linear and you discover through algorithmic testing that a relationship is nonlinear, which I will have some examples of that in the code exercise, I think, for today. We'll go through that. Then, the researcher who's developing a theoretical explanation should have a notion of why it is that a certain relationship exists in the data, even if it doesn't fit with their theory. Okay, so we had another comment in the chat. That's right. So Martha says that agreed that ML provides opportunities for new insights, patterns, decisions, but also the option for conclusion that whose are incorrect. Evaluating accuracy becomes very important. That's right. So this is a lot of nuances in the just sort of like the development of models with predictive objectives. So we'll actually just jump into some discussion of that now. All right, so prediction as a goal in machine learning. And so we'll talk about a lot of the upsides and downsides of that. Okay, so most of us are probably familiar or experienced with statistical modeling of data from one perspective or another. So we see sort of three objectives that arise in developing statistical models for data. One is just to describe or explore the data, right? So what distribution does the data have? Does the data set have? What are is it fit well by a normal distribution or a Laplace distribution? What is the right kind of model for data? Then the second and most common in most scientific fields is to explain with data to understand what relationships exist and how those relationships fit with theoretical expectations. And then also to predict, right? If we want to predict where arrests are going to occur or want to predict earthquakes or something like that, the goal then is to just develop a predictive model. And importantly, that our research design and modeling choices should be adapted to this objective. What kind of data we're going to have to collect and how we're going to use it in our model development will depend on the objective in using the data, using the statistical models. Okay. So there are important differences. Like I said, explanatory modeling is probably more familiar to most of us, and there are some important differences between explanatory modeling and predictive modeling. So when you're doing explanatory modeling, statistical model is a sort of careful operationalization or representation of a theory. The parameter estimates, so for example, the regression coefficients in a regression model are the objects of interest. We're just using the data to get at those estimates. And the statistical model itself is our object of interest. And variance is less important than bias, meaning the variability in estimates from one study to the next is kind of fixed by the scope of the research that we can conduct. And we just want to make sure that whatever we're doing does not exhibit bias. With predictive modeling, the objects of interest are the values of the variables, right? We want to be able to predict variables on their own scale, predict values of variables on their own scale. The statistical model that we use is chosen to produce the best predictions. The model that we're using doesn't necessarily correspond to any theory. Usually you have theoretical insights that help pick the data at least, but that may not even be the case in some contexts. And prediction is usually prospective. So we're trying to produce predictions outside of the data set that we've gathered rather than effectively predict the variables the observations that we've already gathered. And variance is possibly more important than bias. So in developing predictive models, oftentimes we accept some degree of bias so that we can get less variable predictions and have more accurate predictions. Okay, so this is just an example here of a study by Choi et al., where prediction in and of itself is an interesting application. So on the x-axis of these plots are timelines where important historical events are marked. And on the y-axis is a measure that NLP, natural language processing-based measure that Choi et al. Developed of threat words used in major newspaper articles. And their point in this study was to show that if you kind of tracked the prevalence of these threat words in the news, that they were predictive of major violent upheavals in society. And there's sort of pieces of evidence towards that. So the goal here, again, was not necessarily to test a theory, but just to see if they could extract signals from the news of major disruptive violent events that would occur in the real world. So the goal here is prediction. Okay, so I have two questions about the concept of variance. So I'll just stop here and talk about this a little bit more. Well, I'll get into this a little bit more, but variance here, I mean, the level of uncertainty in our estimates, or level of uncertainty in predictions. So that's most commonly reflected in statistical models as a standard error of an estimate. So if we've seen, I could talk about this specifically when we go through regression, but if you've seen a regression, you have an estimate of a coefficient, and they have a standard error of that estimate. So variance here would be how large that standard error of the estimate is. When it comes to variance in prediction, you could think of variability or standard error of the predicted value for a variable. It could also be promulgated also the question about the variance in the residuals. The variance in the residuals is largely determined by the underlying variance in the data you're trying to model. But this is more in reference to uncertainty in the values that you're predicting for each observation. So you can formulate a model that has very high variance in the predictions, but you think is an accurate reflection of theory, versus another model that maybe it only uses a couple of independent variables, so it produces a very low variance prediction that turns out to be more accurate. Feel free to ping me on that again if you want further explanation or if it's still unclear what's meant by this concept of variance. Okay, so prediction can also be used in the formulation of explanations. So explanation and prediction they're different goals, but they are complementary in a lot of contexts. So predictive modeling and evaluation can shed light on new relationships that require explanatory treatment. So if you discover a nonlinear relationship or something interesting in the data that you didn't think about when you were conceptualizing what you expected to happen with the data, that begs explanation. It can help in comparing alternative measures of the same construct. So I'm in the field of political science, so there are many different measures of, for example, how liberal or conservative a politician is. And one of the most common ways of comparing different measures of the ideological position of an individual or a lawmaker is to see how well different measures predict their voting. So the prediction can be used to compare theoretical claims, right? If you have one theory and another theory, formulate two models based on them, see which one predicts best. And also prediction can be used to assess the distance between what a model says should happen in the data and what is really going on. And predictive methods can be used to quantify the predictability of a phenomenon. Again, in political science, a lot of researchers focus on the problem of predicting war, predicting conflict, whether or not there will be a conflict between two countries or whether there'll be a civil war in a given country. And there's a lot of debate over just how well we could actually do, how predictable is the phenomenon of military conflict. Cyrus has a comment about the trade-off between variance and bias. And so that's certainly true. So what's the issue here that often arises that you do have a trade-off between variance and bias. And so if you want to make sure that your model captures the true underlying data generating process. That often means adding a lot of variables to the model, which can increase variance. But if you want really clean, accurate predictions, you usually weed out a lot of the variables that you think otherwise should be in the model, and you end up increasing bias by omitting variables from the model. So there is a trade-off there between bias and variance. And if we're focused on prediction as the goal, oftentimes we're willing to accept some bias in the model in order to get that predictive accuracy and reduce variance.